Hello and welcome to The Naked Scientists with me, Chris Smith, and with Kat Arney.
This week, we're taking a trip back in time to find out what the climate was like millions of years ago. How has the status quo shifted since the Industrial Revolution? And what role have the oceans played?
Plus, in the news this week, a new species of early human ancestor, the scientist who's jumping the Hubble queue with a helium balloon, and why humans are hardwired for laziness, it seems.
The Naked Scientists podcast is powered by ukfast.co.uk.
First up, where we came from is arguably one of the most important questions facing mankind, and this week the story has become even more intriguing. The well-preserved remains of 15 individuals from a new species of human ancestor called Homo naledi have been unveiled by scientists in South Africa. The name means star in local language, and it's a nod to the Rising Star cave system where the remains were uncovered.
These primitive people show features very similar to our own. Their hands and feet are almost identical to a modern human, but their heads and brains were much smaller. Their shoulders were tilted ape-like to favour climbing, and their pelvis was proportionally wider than our own. So therefore they share a number of key features with us, but are also clearly distinct and less evolved than us, suggesting that they might sit very early in our evolutionary timeline.
The finds also harbour another secret. It's possible that these individuals might have been put where the scientists found them after they died. I spoke with the discoverers Lee Berger from the University of Witwatersrand, Charles Masiba from the University of Colorado, and up first, Wisconsin-Madison University's John Hawkes.
If you looked at Homo naledi from some distance, they would stand about 1.4 meters high, the size of a small human. They stand upright. They're very thin-looking in build, and as you look closer, you notice that there's some things wrong about them. Their heads are very small. Their heads are around a third the size of ours in terms of their brain size. Their hips are cast much more like a more primitive hominin, something like Lucy, the famous skeleton. Their shoulders are sort of canted upwards in a way that we associate with some of the most primitive hominins. We think that that's probably related to climbing. But it's very clear that when you look at the details, the things that strike us as being so human-like, the feet, they're clearly adapted for walking long distances in the way that humans have. Their hands, very human-like through the wrist and the palm. Their thumb is appropriate for humans in its length, but the fingers are very curved, and that thumb is immensely powerful, something that we've never seen before in the fossil record. Their teeth also really quite human-like in their size, in what they look like they would have been suited for in terms of eating, but they have features in them that we've never seen before in humans or any other kind of hominin.
And Lee, how did you find them in the first place?
Well, they were found as part of an organized search. I'd actually enlisted a former student of mine, employed him to actually be going underground in the caves just outside of Johannesburg. He, in turn, enlisted two amateur cavers, Rick Hunter and Steve Tucker. And what that led to in mid-September of 2013 was Steve and Rick entering a very tiny, narrow passage about 20 meters underground that's about 17 and a half centimeters wide, dropping down 12 meters into a chamber where they chanced upon this remarkable discovery. I saw the first photos on October 1st. That led to a 60-person expedition that we launched on November 7th, which led to the recovery of this remarkable sample of fossil hominids.
Well, when you saw that photograph, just describe the scene for us in that situation. What did you see?
I was at home at night, 9 o'clock in the evening, working on some emails, and the doorbell rang, and there was Pedro on the other side, and he said, "You're going to want to let me in?" And I almost didn't, given that tone. And he came in with Steve in tow, and they opened up this laptop, and there sitting in the middle of this picture was a mandible. That's a jawbone with these beautiful teeth that I could immediately tell were from a very primitive or ancient hominid. I could tell by the shape of them. The next slide was that of a skull, or at least half a skull, embedded in the dirt of the ground. And just to say, we don't see fossils like that in southern Africa. Most of our fossils are embedded in concrete-like rock. These were sitting in dirt loose. The next slide was of more bones, and I thought I was looking at a skeleton. I was stunned. I'd never seen anything like that.
And Charles Masiba, who's also part of the team from the University of Colorado, when you look at those teeth, where do they fit in?
Well, when you look at those teeth, you realize that they are not modern humans. They have some features transitional between modern humans and some of our earliest ancestors. It's very interesting in that it may be signaling some completely different type of adaptation to maybe a different type of dietary behavior, which may not necessarily be exactly like ours.
And John, given where these specimens were found, how do you account for them being there?
You know, this is the thing that occupied us as we were excavating. This is the largest assemblage of bone that we've found for early hominins anywhere. And we've found them together with no animal bones other than a few little fragments. So there's something very curious about the way that these hominins entered this chamber. There's no evidence that these bones were ever altered or chewed on by carnivores. It's clearly not some sort of predator that's dragged them into this cave. There's no signs of it at all. We've looked at the sediments within the chamber where we find them, and we can show that those sediments originated within the chamber. They don't have grains that have come from the external environment, and in fact, the nearby chambers don't have grains that have come from the external environment. We look at that, and we think it's very likely that the entrance to the chamber in the past was always pitch black and isolated from the outside environment. That explains why other creatures besides the hominins were not able to reach the chamber, and it creates a problem in that Homo naledi has to have been able to access the entrance of this and reach it inside with bodies.
So you're saying that these pretty primitive, small-brained individuals must have been intentionally depositing either themselves or they're dead or dying in this chamber, and then they remained in situ for you to find potentially up to 2.5 million years later.
What we were working in here is a bed that's full of hominin bone, and that includes articulated elements like complete hands and feet, things that would have been disarticulated rapidly if the bodies had not entered this chamber whole. We've got them in a situation where they could not have been washed in, where there's no evidence that there's a catastrophe that's happened to them, where they've clearly entered the chamber over some period of time. We don't know how long, but not instantaneously. We can, in other words, exclude the things that seem simple, like some sort of catastrophic event, some sort of flood, some sort of predator that's a death trap that's had them fall in. We're left with the explanation that Homo naledi itself must have been intentionally depositing bodies at the entrance of this chamber or into the chamber itself.
Do you think this is cannibalism, possibly? Could these have been a future lunch?
We have examined every bone in microscopic detail, and there's no sign on them that they've been cut upon, that they've been chewed on. The only marks we find on them are the marks that come from natural decomposers, like beetles and snails. So we can totally exclude that this was some sort of violent, aggressive event, or that they were cannibalizing each other. The evidence is just totally against it.
And Charles, can you dig into some of those sediments and some of the context in which these remains are found and begin to refine the date from which they probably do hail?
The geology of that cave is very complex, and we have to also think about the nature of the deposit itself, how those bones were actually deposited. So we have to reconstruct that deposition history, and then we have to look into the timing. So it's painstaking work which has to be done. Unfortunately, we're still working on that, and we are not in a rush to try to actually come up with quick dates. This is an assemblage which is very unique. It's so different. We can start to see things which we have never seen before. Rather than being blinded by dates, we're not going for that quick shortcut.
And Lee, given the incredible state of preservation of these fossils and their sheer number, where do we stand on trying to get DNA out of them? You've got these pristine teeth and so on.
The next phase of this project is going for questions like that. Right now, ancient DNA discoveries have been restricted to the last several hundreds of thousands of years. I think we've pushed it maybe back to 500,000 or 600,000 years at this stage, but under remarkable circumstances. But this is a remarkable assemblage. And maybe we'll be talking to you in the near future and saying, guess what?
And John, how are you now seeking to share this with other scientists in your field, but also the world?
Well, Lee, of course, has long been a leader in this. And from a science point of view, we can say in a very straightforward way, here's the bones that we're finding, but the development of interpretation of, are these something that we've seen before or something new, took us many, many months. To conduct that process, we wanted to open it to a broader scientific community to allow more participation in the analysis of the bone. We specifically engaged early career scientists from South Africa and around the world. And we brought them to Johannesburg to cooperate with Lee's team and really created a dream team of people who had enormous expertise in describing new hominin remains. And now, of course, we're doing everything that we can to share them even more broadly. We have three-dimensional images of these that you can examine, and you can print them out on computers, and we're making them available on a site called Morphosource so that people can access them. We're doing everything that we can to share every aspect of this discovery with the public and with other scientists and with school teachers.
Also, these fossils are right now on display at Maripang, and I think that is unprecedented. From the moment of the press conference, we've put the largest assemblage of fossil hominins on display at our visitor center in the Cradle of Humankind, where people can actually go and stand next to this extraordinary discovery. In addition, every person on this planet can actually download these papers and see the science themselves. We've published them in a journal called eLife, which is an open source, open access journal, and we did that deliberately because it was a good fit with our team's ethos, that is, of sharing this with not only the scientific community, but the public at large.
Incredible work. Lee Berger, and before him, John Hawkes and Charles Masiba, talking to me from Johannesburg earlier this week. You're listening to The Naked Scientist with Chris Smith and also with Kat Arney. If you'd like to get in touch, it's chris@thenakedscientist.com.
Fakes, whether they're cancer drugs, car parts or anything else, are a big problem, costing economies billions of pounds worldwide and potentially endangering lives. Counterfeiters are also clever. They quickly work out how to get round measures that manufacturers put in place to tell apart genuine goods from cheap knockoffs. But now a new three-dimensional barcode created by engineers at the University of Bradford working with the company Softmat could be a new way to uniquely stamp individual pills or products. Elaine Brown was one of the team behind the new technology, which was revealed at the British Science Festival in Bradford this week.
When we think of anti-counterfeiting, a lot of the time we think of it as being a problem for big business, but actually it affects all of us. We want to know that when we purchase something or when we use something, then it is real and we can trust it.
And what sort of things are we talking about? I might see someone walking around with a Prada handbag and go, is that really real, or are there other things as well?
Well, that kind of thing is, of course, important. It's very important to the companies that make those products. For me, where I see it's a real important thing for me as an individual would be something that would have a direct effect on me, such as a drug, a medicine, or something that I would put in my body, like an implant, or, for example, part of a car that I'm driving and I want to know that if I put a spare part in, that it's real and it's not going to fail.
Tell me about the technology that you and your colleagues and your collaborators have been developing to try and put markings on so that we know that these products are real. How does this work? What is it?
We work on something called micro and nanotechnology moulding, which basically means moulding really tiny things or moulding large things but with tiny features on them. So we can put something on a part, on a moulded part, that can't be seen by the naked eye. It's really tiny, and we can put such detail on that, we can mould such detail into that, that we can tell sequentially where something has been made, where something has been manufactured, what number it was in the batch, for example. So because of that, we can use the high technology moulding equipment to produce something that can mark individual tablets, for example, or individual parts.
How does this actually work? What is the mark? What would it look like?
Under the scanner or the reader, we would be able to see a series of markings that not only had a pattern on the surface but also were at different depths. Now, we can put different markings on, different barcodes on something afterwards, but it's very unusual for the barcode to be integral to the part, but also have different depths at very, very small steps so that we can read them back with high technology equipment.
Can you explain a little bit more about how this actual marking works? What does it look like at that nano level?
Well, in the moulding machine, we have a mould cavity that has lots of surface features on it for whatever we're trying to make. As part of that, we can put some pins which will move. The pins that we use go into the mould, and we can have an array of pins, and we've used 4 to now, but we can use more pins than that. We can set them at different heights. Now, those height levels are very, very tiny. We wouldn't be able to detect them by sight or by touch. So we're talking about 40 to 50 microns. And when you think that a human hair is about 100 microns in diameter, these are very small steps. We have to be able to set those steps, and we have to be able to mould the polymer to an equivalent step. And that's quite difficult to do, but with expertise at Bradford, we can do that. So because we then have lots of different heights for our pins, and we can increase the number of pins we have millions of different combinations. It gives us a very, very large number of different markings that we can put on our pills or on our mouldings.
So that's the marking, but what about the reading? Many of us are familiar with the supermarket scanners where you hold up the barcode, like, bip, there you go. Would that be a similar kind of idea? You'd put a pill in something, it would go, bip, yep, that's real.
Yes, you would put the moulded pill into a scanner. Generally, if we look at the kind of barcodes that we have in the supermarket, there are just 2 levels. There's usually black and white lines. So what the reader for this particular device would require, and the reader that's being developed, allows us to measure the depths as well as the different pattern in a 2D way. So that gives us the 3D pattern.
Why is this so important to the pharmaceutical industry? I've got a packet of off-the-shelf painkillers in my handbag. I'm presuming it wouldn't really be worth marking all of those. What kind of drugs would be marked, and why is that important?
There are some very, very specialist drugs on the market. It's important that the companies that develop them know that they are not being copied and sold by counterfeiters, but it's also important to us as users of those drugs. If we added something to the drug to mark an individual drug, then that would be very difficult. We'd be adding something that would contaminate the drug in some way. This particular technology is so exciting because we're moulding it into the individual drug.
What's the financial scale of counterfeiting?
We're talking a lot of money here, millions and millions of pounds. For us as a university, the financial side, of course, is important, but it's also highly important to us that we can, as engineers, protect the public, protect society from counterfeiters. It's a huge problem. It is the money, but it's also our safety.
Elaine Brown from the University of Bradford.
Hello, Controller. Are you ready to begin?
The Space Boffins are joined by 2 astronauts and the space scientist who knows how to rock a beard. Who else could it be but Rosetta Project scientist Matt Taylor, to fill us in on the next stage of Europe's comet-chasing mission. We also hear from NASA astronaut Cady Coleman discussing sustainability and the future of our planet, and former ESA astronaut Thomas Reiter on the future of the European Astronaut Corps. Add astronomer Robert Massey, and you have the latest Space Boffins podcast in partnership with Naked Scientists.
This is The Naked Scientists. I'm Chris Smith.
And I'm Kat Arney. Still to come, why you're pre-programmed to be lazy, and an in-depth look at our oceans and their role in the planet's climate.
But first, into outer space. One of the big mysteries that scientists are grappling with concerns dark matter, which accounts for 20% of the mass of the universe, but we have no idea what it actually is. We know it's there because we can see the effects that it has on other things that we can see, like stars. But to study it, we first need to plot where it is. One way to do this is with the Hubble Space Telescope, but the queue is pretty long. So Richard Massey from Durham University has developed his own approach. He's made a helium balloon that carries a telescope to the borders of space. Sam Mahaffey caught up with him in Canada, where he's busy preparing to launch.
Dark matter is this weird stuff that's out there in the universe. In fact, it's the most common stuff in the universe, and it's the heaviest stuff there is. We know it's there because all of that mass and all of that gravity pulls around things that we can see. And so all the stars in the Milky Way are spinning round and round and round because of dark matter. But unfortunately, the dark matter itself is invisible. So we can't see it directly. We have to infer it's there because of the way it moves things we can see. And to be honest, it's become a bit of a mystery, almost the biggest mystery. We just don't know what this stuff is. And, well, we're trying to find out.
If it's so hard for you to observe, how do you study it?
The best way that we've found to look at dark matter is through a technique called gravitational lensing. The idea of this is that you don't look at the dark matter itself, you can't because it's invisible, but you look at something behind it. And the effect of this is like looking through a sort of a funhouse mirror or looking through a bathroom window pane. When light doesn't travel in straight lines, then the object behind it appears a bit distorted. So when you look out of a bathroom window, the streetlights on the other side of the road look all wobbly and they don't look light-shaped. Well, when we look past some dark matter, the galaxies behind it don't look galaxy-shaped. They look all distorted and stretched. We can infer from that there must be something very heavy in front of them. And if we can't see anything, it must be this dark matter that's invisible. If we have a telescope in space, like the Hubble Space Telescope, then we get a perfect view of them and we can measure their shapes and look how distorted the light is.
But you're going to some really quite extreme lengths to observe dark matter when you could just use the Hubble Space Telescope.
Well, we've used the Hubble Space Telescope for this kind of stuff before, and it's a fantastic instrument. Unfortunately, there's a long waiting list to use the Hubble Space Telescope. Everybody wants to go. And we basically got sort of bored waiting and said, wouldn't it be nice to have our own satellite, our own telescope in space? Unfortunately, in these times of austerity, we can't afford a whole satellite in space. But we got inventive and thought, well, we can get 99% of the way into space with a big helium-filled balloon. If we sling a telescope underneath that, well, we're above basically all of the Earth's atmosphere, but it's a lot cheaper, a lot easier. And so that's what we've done. It's going up to about 100,000 feet. That's about 3 times higher than a plane. And it goes straight up and it can lift a lot of weight, including our telescope. Now, the big problem about putting a telescope underneath a balloon is that you've got a great big balloon, then a sort of 100-meter long rope, and then a telescope swinging around underneath it. And as this telescope swings backwards and forwards, of course, it's moving around. It's pointing at different places. So the clever thing that we've had to do is to develop a way to keep the telescope pointing in the same direction. So we've got this whole sort of series of gimbals that sort of rotate so that the telescope itself is held within several concentric cages. As the sort of gondola that it's in swings around, the telescope itself uses some gyroscopes to stay pointing in exactly the right direction.
But what happens to the balloon and what happens to the telescope when you've finished? Could it just come crashing down to Earth and land on somebody's head?
Well, that's sort of part of the problem with this is the balloon that we're about to launch is going to go up just for 24 hours. It's then going to come down on a parachute and hopefully survive. Now, not all of them do survive. There's sort of half of the time you need to do some repairs, and sort of 1 in 5 times enough of it comes down that you have to basically rebuild it.
And now you've got NASA's approval. Might we detect some dark matter very soon?
We've got the flight now to test that everything works, and we're booked in for a long-duration balloon flight to do lots and lots of science and look for lots of dark matter and other things. That's going to happen in 2017. So we've got a few months to do some repairs and maybe upgrade the odd camera here and there, and then get ready to send it up and start looking for dark matter.
We wish you well. That's Richard Massey from Durham University, ending that report there from Sam Mahaffey.
Now, humans are wired for laziness, apparently. In a new study, volunteers walking on a treadmill under different conditions constantly altered the way they moved to minimise how many calories they burned. Talking with Ginny Smith, lead author Max Donnellan thinks this is likely to be a trait our ancestors evolved when food was scarce.
There's an infinite number of ways to get from point A to point B when you're walking. But people have a preferred way of doing it. They prefer a certain speed. They prefer a certain step length and step frequency. They prefer a certain step width. And it turns out their preferred way of moving minimizes their energetic cost. And when I say energetic cost, I mean literally the amount of food needed to get them from point A to point B. And the question was, even though they had millions of steps experience with their normal way of walking, would they be able to learn the gait that's now cheaper to walk at? how quickly would they learn it, and for how small of savings would they do it for.
The team, led by PhD student Jessica Selinger, put participants on a treadmill moving at a constant speed and measured the amount of oxygen they consumed and the carbon dioxide they breathed out to calculate their energy consumption. Once they'd determined each participant's preferred step frequency and how efficient it was, they then had to do something to make that preferred way of walking more energetically demanding. To do this, they used a special kind of exoskeleton.
There's one in each leg, and they look like a very high-tech athletic knee brace, if you will. It has gears and a motor, and then we can use those gears and motor to apply a resistance to the knee joint when people are walking that we can control almost in any way we like to. And so in this case, we control the resistance as a function of people's step frequency. And that resistance makes walking harder. And so we can make it so that the resistance is higher at high step frequencies and lower at low step frequencies, so that we're penalizing high step frequencies. The idea is this would shift the energetic minimum to be at lower step frequencies than what people normally prefer. But we can also give the control function in the opposite direction and shift in the other direction. So the idea is it allows us to give people new energetic landscapes that render previous predictions about what the right thing to do is, the energetically optimal things to do is, obsolete. And then study how people navigate these new energetic landscapes and whether or not they're able to converge on the minimum in these new landscapes, all accomplished with these exoskeletons.
The results show that people did indeed adjust their way of walking to expend the least energy possible for the conditions they were under. When food was scarce, it made sense that our ancestors would have evolved to preserve as much energy as they could. I wanted to know if Max thought that that was what was going on here.
We don't know for sure that that's how we evolved the system and why we evolved the system, but it does make some rational sense that if you moved as cheaply as possible when you're hunting, then you could spend less time hunting, less time exposing yourself to predators, more time reproducing, all the things that increase your evolutionary fitness. So it does make some sense that you'd like your nervous system to be helping you in the background to make sure your movements are cheap. But I should add, it does it for a surprisingly small savings. So that was one of the remarkable things about the finding, is that the nervous system was fine-tuning to gain as small as a 5% change in energetic cost. And so if you're walking for an hour, that savings adds up to be about a peanut worth of calories or kilojoules. That's a remarkably small savings, literally peanuts of savings.
While a peanut worth of saved calories hardly seems worth worrying about, this study shows that without us even realising it, our nervous systems are constantly monitoring our way of moving and adjusting it subconsciously. This may have been great for our ancestors, who were trying to save energy, but for most of us in the modern world, we'd prefer to burn more calories, meaning we're actually fighting against ourselves.
If you try to change your way of moving in some way during this to make it even more expensive for you, what you'd find is that you'd be working against your nervous system in doing so. Let's say you put heavy weights on your feet or something like that to make it more costly for your exercise. But what your nervous system is going to do is try and figure out, while you're doing the activity, how to adapt your way of moving in order to make that cost as small as possible. So it's not that you can't add a cost to it, but it's good. Your nervous system is going to try and reduce it by as much as it can.
Max Donnellan from Simon Fraser University, and that work was published this week in Current Biology. In response to our tweet, "Did you know your nervous system wires you for laziness?" both Ian and Norma Laming came straight back to say, "Well, I didn't, but I couldn't be bothered to reply to tell you whether I thought it was true or not."
This is The Naked Scientists with Kat Arney and Chris Smith.
Now, climate change and concerns about rising levels of carbon dioxide in the atmosphere are very often in the headlines. It was announced recently that the monthly global average concentration of carbon dioxide recently exceeded 400 parts per million for the first time in human history.
But we have been here before. Similar levels of CO2 were probably present way back in history, long before humans even evolved. And the climate's also been changing for millions of years. So should we worry now?
To answer this question, we need to understand what causes these natural variations in atmospheric carbon dioxide concentration and how this in turn influences the climate. To do that, we need a way to look back into the past to work out what the climate and carbon dioxide levels were doing, which is what Cambridge University's Julia Gottschalk works on. So Julia, how do we know what was happening to the climate millions of years ago?
We have a variety of climate archives that we can study in detail and that record the past climate. So, for instance, there are these beautiful ice cores from Greenland and Antarctica. And these ice cores basically comprise of snow that has fallen in the past and that accumulated over time. And for instance, the isotopic composition of that snow can tell us something about the air temperature in the past.
So there's a sort of chemical fingerprint written into there that tells you at a certain time back in history, this is what the temperature of the Earth must be when the water that led to that snow was around.
Exactly, yes, exactly.
What else is in the snow? Are there any other things trapped in there that we can measure?
Yeah, so luckily the snow has enclosed air from the past. So there's
like little bubbles?
Yeah, we can actually measure the chemical composition of that air. So we exactly know what the carbon dioxide concentration was in the past.
How do we know that it hasn't changed after the bubble gets trapped in the ice?
The way it can actually change is by diffusion through the ice. It's the only way, because the ice encapsulates the air bubble, right? But we know that the diffusion is very, very low and very little.
So it should be really trustworthy.
It is very trustworthy.
And
yes.
How far can you go back with an ice core?
Our longest ice core goes back to about 1 million years ago.
Not very long. Can we go back further in any way, with any other markers or measures?
Yes, so we have sediment cores from the seafloor. And these comprise of particles that have accumulated in the past ocean, but they also save or capture creatures that lived in the past ocean. And I have been working on so-called foraminifera, that are tiny creatures that are comprised of calcium carbonate. So
they have a little shell.
They are very beautiful fossils, basically, and they have very delicate shells.
And again, you can look at the chemistry of that shell.
Exactly.
To work out what must be happening to the carbon dioxide level in the atmosphere. It's like a proxy measure.
Not for the carbon dioxide, but you must imagine the foraminifera lived in the surface ocean. They basically record the properties of the ambient water they were living in. So, for instance, the temperature, possibly the salinity as well, pH of the seawater. So what we can do is measure different proxies to reconstruct these properties.
Now, the cynic in me is saying, fine, so you look at these ice cores, you look at these bubbles of trapped gas in the ice cores, you look at these foraminiferae and look at the chemistry of their shells, and you say, I think this is what's going on in the climate when they were alive. How do you validate that? How do you say, right, independently, I can confirm that that is the case?
This is a very important task that we have to do as scientists, right? But one approach that we usually adopt is to look at different locations on the globe, but also to use different approaches, different proxies. And if very different proxies show the same trend, then we can actually be very confident in saying that the trend is actually robust.
One's corroborating another, I suppose.
Exactly.
When you look at these independent measures over long geological timescales, what do they show that the climate has done and the ocean chemistry has done over these long periods of time?
For instance, let's say we go back 100 million years ago, for instance, during the time when the dinosaurs lived. So we know that the Jurassic and Cretaceous atmosphere was much higher in CO2. The global temperature were much higher. But we also know that the climate since then followed a global cooling trend.
But what would have driven that? Why would the CO2 level have been extremely high and then gone down, and temperatures with it?
Tectonic activity was much higher, yeah. So seafloor spreading was much more active. So the CO2 that were outgassing from the mantle at that time was evading into the atmosphere and was
So there was more production of CO2. The other thing that can pull CO2 out of the atmosphere, though, is mountains, isn't it? If you get weathering of mountains, this can chemically react. So was that also responsible for a drawdown of CO2?
Yeah, absolutely. For instance, the formation of the Himalayan plateau. India was colliding with Asia, and the uplift of a lot of rocks at that time and the formation of a lot of rocks at that time interfered with the atmosphere. And as you said, the silicate weathering pulled a lot of CO2 out of the atmosphere, and that helped to bring global temperatures down over time.
And if you look at what your markers and proxies have shown the atmosphere and the oceans have done chemically and thermally over time, and you ask, how does the climate today compare with what your proxies would suggest should be happening?
Let's consider, for instance, the past million years. We have known that the climate has shifted very frequently from a cold climate state to a warm climate state. So sea level has changed in time with it, and also CO2 concentration have changed in time with it. And considering that this sort of rhythm would happen in the future, we would expect that soon we will go back to a cold climate state again. But with the changes in anthropogenic CO2 emissions, this might be very different now.
Are you saying the world should be getting colder based on past measures and past cycle behaviour? In fact, it's not. It's actually getting warmer, and also the CO2 in the atmosphere should be going down, it's going up.
That's correct, yes. So what is actually quite worrying is the rate of the climate change. So we have never seen the climate system change that rapidly as we observe it today. So that's quite worrying. We know that an interglacial climate state has actually lasted for a certain amount of time. And after that amount of time, we would expect that the climate system would go back to a glacial. But I would not be so sure that this will happen now with changes in the chemistry of the atmosphere that we might have caused.
It's very worrying, isn't it? Thank you very much, Julia Gottschalk from the Department of Earth Sciences in Cambridge.
As the world warms and atmospheric carbon dioxide levels increase, a significant proportion of this extra energy and CO2 enters our oceans. They act like a giant sponge, storing the heat and carbon, which they then redistribute around the globe, influencing climate elsewhere.
But what controls how water in the oceans moves, and how is this linked to climate? Well, Jo Kerr rolled up her sleeves and went to find out.
Hi, Alex. How are you?
My name is Alexander Petrowski. I'm a lecturer in earth sciences, and I study past changes in ocean circulation. The global ocean circulation has been likened to a conveyor belt, where deep water masses flow from the Atlantic primarily through the Southern Ocean into the Indian Ocean and the Pacific Ocean. We make deep waters by either making them more salty or more cold. They become dense and they sink into the deep ocean. This is going to happen near the poles primarily. What I'm making here is average ocean water. I have a 10-liter bucket of tap water, and I'm going to be adding 350 grams of salt in total. Now I have to pour this into the tank. So this tank is basically the average composition of the ocean, and we're going to be now adding different parcels of water that have different temperatures and salinities, so therefore different densities. What I'm making now is similar to the types of water masses you'd find at intermediate depths in the ocean. They are formed from relatively warm, salty surface waters. We're also going to make cold, salty water, and we're going to dye these in different colors so we can follow their circulation through the tank.
This is our warm, salty water?
Yes.
Okay, let's dye this red.
So I'm basically using a funnel to add the water to the tank, okay, and so that prevents it from vigorously mixing with the average seawater, so it maintains its temperature and salinity.
So it was flowing to the bottom, and now it's started to rise up, and it's actually forming an intermediate parcel of water.
So what we can see is that basically this red water mass is flowing along the middle of the tank. It's basically found the depth at which it has the same density as the surrounding water and is spreading along a surface of that density. In the ocean, those surfaces we call isopycnals. We can mix along isopycnals, and it's much more difficult to mix vertically. You can see this if we add some cold, salty water with a different color. What color would you like to make the very dense water?
I think we should go for blue. At the other end of the tank, we're putting in the cold, salty water, and this is sinking much quicker, and it's sticking right along the bottom.
Because basically the ocean is density stratified, and what we're adding is very dense water. It's very cold and salty. So if you looked at the temperature and salinity of the Atlantic Ocean, you'd see a very similar picture to what we're seeing in this tank. The red water would be analogous to water mass we call North Atlantic deep water, which forms in the Nordic Seas near Iceland and the Labrador Seas near Greenland. It is subducted down to about 3 kilometers and flows southwards. The blue water mass is analogous to Antarctic bottom water, which forms near the edge of the Antarctic ice sheet by supercooling of Southern Ocean waters, and it flows at about 4 to 5 kilometers northwards into the Atlantic Ocean. And we could see that there's a strong gradient in the color between them. And that basically means that these water masses are not mixing with each other.
Is this how the currents are moving around the whole ocean, or is it just the Atlantic Ocean?
When we form deep waters and we circulate them through the deep ocean, we have to replace those waters with surface waters. So the surface ocean circulation is linked to the deep ocean circulation. And the surface ocean circulation includes things like the Gulf Stream, which transports heat from the equatorial regions towards the poles. Deep water masses often contain a large amount of carbon and other nutrients. And so that carbon is being kept out of contact with the atmosphere and being stored in this reservoir of deep waters. So in our analogy, the blue water mass would actually, in the real ocean, contain a lot of carbon. And at times in the past, it may have contained more or less carbon. And that carbon, which would otherwise be in the atmosphere, is stored in the deep ocean. So it's linked to the CO2 concentration of the atmosphere, which is a known climate amplifier.
So if we can store more carbon in the deep ocean, this is effectively influencing our climate through the atmospheric concentrations of carbon dioxide. Is that correct?
Yes, that's correct. And basically what we'd expect to see if we look in the paleo record is that we'd see that changes in circulation would be closely linked to changes in climate. Changes in climate can affect the temperatures and salinities of the deep waters that we form. So for example, we can increase the amount of sea ice, or we could change the amount of convection within the ocean, and the deep water masses would respond to that climate forcing. However, changes in the circulation through its transport of heat and the amount of carbon that's stored in deep water masses can affect climate.
Does that mean that it's not only the climate affecting the oceans also affect the climate?
So the Earth's climate system is not just a simple linear equation. There are feedback mechanisms between the physics of ocean circulation, the chemistry of water masses, and the biology that inhabits the ocean. And that's why we need to rely on both paleo proxy records to reconstruct the history of the ocean, and also use computer models to understand how these feedbacks relate to each other and how they may have changed in the past and how they may change in the future.
Cambridge University's Alex Petrovsky. He was speaking with Joe Kerr. You're listening to The Naked Scientist with Chris Smith and also with Kat Arney. If you'd like to get in touch, it's chris@thenakedscientist.com.
So far, we've heard why the oceans and the climate are inextricably linked. Changes in climate impact on the seas, and in turn, changes in the oceans influence the climate. But has it always been like this? And how would we know what's changed? To find out, we're joined by David Thornalley from University College London. Hi, David.
Hi.
So has it always been like this? We've heard about the circulating currents that we have now. What do we know about the situation in the past?
No, it hasn't always been the same circulation as we see today. As we've talked about earlier, there's been these swings in climate between warm interglacial climates and cold glacial climates. And we think that these swings in climate are associated with different styles of ocean circulation as well.
Can you give me some examples of what we know has changed in the oceans over, I guess let's start with a really big timescale.
Yeah, so if we start with this glacial interglacial 100,000-year timescale of climate change, one good example to start with is if we looked at the Southern Ocean.
What kind of area are we talking about here?
So the Southern Ocean, it's the bit at the bottom of the globe, the ocean surrounding Antarctica. And this is a really important part of the ocean today because it's where this deep water that's rich in dissolved carbon dioxide can upwell and come to the surface. And there it releases its carbon dioxide to the atmosphere.
What do we know about the way that that's changed then over this kind of 100,000-year timescale?
Yeah, so we think that in the past, the amount of upwelling of this carbon dioxide-rich gas has changed, and we've lost some of this leakage of CO2 in the past. So in the glacial climate, one example we think has happened is it was a lot colder, and we had an expansion of sea ice around Antarctica, and that acted as a cap to keep CO2 trapped within the ocean. And it's almost, you have this feedback between the ocean and climate, whereby climate's colder, you grow sea ice, that means you cap more carbon dioxide in the ocean. That in turn means the climate gets colder and we grow more sea ice, draw down more CO2. And you can get into quite an extreme state of a very cold glacial climate.
But we're not like that now. Obviously, we have a much smaller ice cap down in the south. So what do we know about what happened to tip that change, and how have things changed since then?
There's natural drivers of climate change, changes in the way the Earth's orbit, that can help start off these feedback processes. And so we were able to get out of the glacial by this sea ice gradually melting back. And we just run that feedback process in reverse. The sea ice melts, that allows some CO2 to come out, and we feedback on that process until we get to a current warm climate like the current interglacial that we're in today. So we have this seesawing back between cold and warm glacial climates.
So that's on the scale of hundreds of thousands of years. What about wobbles, changes in the climate, or maybe a scale of 1,000 or even hundreds of years?
Yeah, so another interesting area we can look at in how the ocean influences climate is if we switch to the other area of the globe. If we go all the way now to the northern North Atlantic, this is an important area where we have warm surface waters flow northwards and they sink and flow south. This is like a big ocean conveyor belt that sends heat northwards and helps keep Britain and Northern Europe warm.
Woo!
Exactly. And we think that the strength of that conveyor belt may have changed in the past. Well, we know that on the big scale it has weakened in the past. But then the big question is, on these shorter timescales, these century timescales, have wobbles in the strength of this conveyor belt influenced our climate?
Because I remember seeing pictures, of in medieval times, they were skating on the Thames and all this kind of thing. Was that linked to these smaller changes?
Potentially, and a lot of people are trying to research that question. But it could be that in these colder climates, there was a slightly weaker conveyor belt that was bringing less heat northwards, and it could have led to these colder climates that we associated with this interval called the Little Ice Age.
So that's sort of hundreds of thousands of years, hundreds of years. Are these changes happening maybe in terms of decades? What kind of short scale can we see these changes on, and why are these important?
When we look at these short timescales, we can think about changes in the water masses we see at the surface. So in the North Atlantic, we have cold Arctic water, and then we have warmer tropical waters making their way northwards. And that balance of what type of water mass you have matters. Different types of fish and different types of plankton live in those different water masses. And so these changing water masses can affect where fish stocks may be. We have records whereby you get incursions of warm water moving up and down the Norwegian coast that are associated with historical documents of different fish yields up and down the Norwegian coast. And so we're obviously interested in those natural variability that we can see today. How's that going to impact where the fish are today?
That's fish. Fish, obviously, very important. But when we look at these wobbles on the short term, the mid-term, the long term, what do they tell us? Because there's a lot in the media about, this climate change, maybe it's just a wobble. How do we know what's a wobble and what's actually worrying?
This is one of the important reasons why we should look at the past, because it allows us to see what kind of variability can we expect. We obviously have to take into account what's driving that variability. And today we're worried about the human influence on the climate. But we want to look at what that natural variability is and monitoring the climate system today and seeing, are we seeing anything unexpected outside the range of what we might expect from natural variability? And that's when we start to see something unexpected. We think, hang on, maybe we need to be aware and maybe we do need to be somewhat concerned. It's not about just these regional changes, maybe Britain being a little bit warmer, which would be nice. It's about these global impacts that ocean circulation can have.
Obviously, a very important area to study. Thank you very much. That's David Thornalley from UCL.
Changes in ocean circulation may have amplified changes in climate in the past, but what does this mean for us today? And if our climate continues to warm, what's going to happen in the future? Anders Liebermann is a climate scientist at Potsdam University in Germany.
If you heat up the atmosphere, you also heat up the ocean, simply because they are strongly coupled. and heat is going all the way from the atmosphere into the ocean and also back. So there's a strong link, and we see this link already. We see the temperature increasing in the atmosphere already for 100 years, and the ocean is also taking up part of this heat and is expanding, which is why sea level is rising. So there's actually no doubt that the oceans are already influenced by human activity.
That being the case, what would be the long-term consequences?
Sea level rise will continue for hundreds of years, actually. But also ocean currents are influenced by the warming simply because ocean currents are driven partially by winds, but also because of the density differences in the ocean. The North Atlantic Current, which is the Gulf Stream once it has parted from the coast of North America, is what we are in Europe particularly interested in because it is bringing a lot of heat to Northern Europe and to the UK particularly. And this North Atlantic Current is then density-driven and can be changed if the temperature of the planet is changing.
So what would be the consequence then if these ocean currents like this one stop working?
The Atlantic overturning is quite unique. If it stops, this heat source is stopped. And you can already see what is going to happen if you go at the same latitude from the UK towards northern Canada, where you have a completely different agriculture. You have actually almost no agriculture there, while you are able to do agriculture in Great Britain. So this is what's going to happen. It's going to get much colder in northern Europe.
If you're not carting the heat off to the northern hemisphere and high latitudes like where we are, where does the heat go?
It stays in the south. So the north gets colder, the south gets warmer, and the sea level changes because at the moment the sea level in the North Atlantic is a bit lower than it should be because of the Atlantic overturning. And once you stop the circulation, the sea level comes up quite rapidly in the north. It'll be up to 1 meter of sea level rise.
This is theoretical, obviously, isn't it? Is there any evidence to support this actually happening at the moment?
Well, at the moment we see a mild decline of the Atlantic overturning circulation. We see this from observations. There have been recent publications showing this again. For the future, we can expect a further reduction in the Atlantic overturning simply because we understand the physics. So if we trust in physics, then we can trust in the fact that the Atlantic overturning is going to reduce if the planet is warming.
What about also the loss of ice? Because we're adding, when you melt ice, a lot of fresh water to the existing salty water. That must also change the density. So does that have an additional effect on currents like the overturning circulation?
If you add meltwater, for example, from Greenland, then you freshen the water and you make it less dense in the north. And then what you can get is actually an abrupt change of the circulation, and thereby an abrupt change in the temperatures of the north.
If we extrapolate this globally, what will be the implications for us as humankind, our ability to feed ourselves, our ability to catch fish and so on?
The Atlantic overturning is really quite a unique circulation on the planet. We have other big ocean currents, but none of them is driven by this kind of extraordinary density difference that we find in the Atlantic. And that's why we don't have to fear abrupt changes in ocean currents, apart from the North Atlantic, which, however, would be a dramatic change, not just for the United Kingdom or for Northern Europe, but for the entire planet. Because the monsoon systems far away, for example in India and China, are linked to this temperature difference in the North Atlantic. And this will actually affect our ability to feed the population of the Earth. For example, in India, if you reduce the monsoon system by just 10%, as we've seen this in the past, you already get famine and a lot of problems economically. So changing something as big as the ocean currents is changing a lot, and humans have to adapt to change, and if it's too quick, it might be difficult.
And is this an inevitability? Is there anything we can do about this?
The warmer we make our planet, the higher the risk of an Atlantic overturning collapse. What we can do is obvious. We can reduce the emission of carbon dioxide into the atmosphere. There are other methods around that are called geoengineering, but they don't reverse what we've done with our climate. They just add another complication to the problem.
Sobering thought, isn't it? Anders Lieberman there.
And thank you to our other contributors this week. That's David Thornalley, Alex Petrovsky and Julia Gottschalk.
This is The Naked Scientist with me, Chris Smith, and also with Kat Arney. And now it's time for our question of the week. Sam Mahaffey has been getting her head around listener Paul's question.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education from Alpha to Omega.
Why do we make mistakes during repetitive tasks?
Well, I definitely do this all the time, especially with tasks I do every day. Sometimes, when I'm making a cup of tea, I throw both the spoon and the tea bag in the bin, instead of just the tea bag. I don't know why I do this. Stephen on Facebook thinks it must be because boredom sets in, and Henry says he doesn't need repetition to make mistakes. Dr. Steve Fleming from the Wellcome Trust Centre for Neuroimaging at UCL has the lowdown.
Well, when we start a repetitive task, our brains set a particular balance between speed and accuracy. So we have enough time to avoid mistakes, but we're not so slow that we'll never get it done. But the problem is that after a while, these tasks become boring and we zone out, thinking instead about what we're going to have for lunch or where we're going to go on holiday. And this is what psychologists call mind wandering or being off task. And we know that this type of zoning out makes our information processing less reliable. But because we're still using that old speed accuracy balance, we end up taking a hit on accuracy and making more errors.
So when our brains aren't fully focused on the task in hand, something's got to give. And if we keep the same pace, we end up losing accuracy. This isn't too much of a problem when I'm making a cup of tea, but these kinds of mistakes can be a really big problem for scientists, especially during lab work or when we're processing lots of data. So, is there any way we can stop ourselves doing this?
Well, it might make sense to start out slower on a repetitive task. So that way, when the inevitable boredom and zoning out hits, you'll be able to carry on without making mistakes. But to really avoid these types of human errors, automation is an obvious way to go. We know that computers are excellent at handling repetitive tasks, and robots can do the same movements again and again without making errors. And this also frees up the human mind to do what it's good at, so think creatively and generate new solutions to problems.
That's really interesting, but I often find that more ideas come to me when I'm doing something mundane, like walking to work or doing the ironing.
Yeah, that's true. So mind wandering often gets a bad rap in the psychology literature. People associate it with something to be cured, and this is in contrast to the more desirable pursuit of focused, rational thought. And our culture also values control and effort, and too much mind wandering has been linked to being unhappy. But there's evidence that some mind wandering is a good thing. So one recent study found that prompting people to mind wander by giving them a boring task actually led them to generate more creative solutions in another task. And many of us experience good ideas just appearing to us when we're not focused on work. So this study supports our intuitions.
Perhaps next time I'm in search of a bright idea, I should just start doing something repetitive, and then maybe it'll come to me. Next week, we'll be trying to answer Katie's very seasonal question.
Why is gooseberry jam red when gooseberries are green?
If you think you know the answer to this question, or if you have a question for us, email chris@thenakedscientist.com, find us on Facebook, tweet @NakedScientists, or join the debate on the forum, nakedscientists.com/forum.
And that's it for this week. Thank you very much to Joe Kerr for putting the programme together. Next week, Kat and I are going to be looking at what it takes to save a life. Every 3 seconds, an emergency call gets made, and it's then a race against the clock to save that person's life. So what does make the difference between life and death? The Naked Scientist comes to you from Cambridge University. It's supported by the STFC, the EPSRC and Rolls-Royce. My name is Chris Smith, and thank you very much for listening. Until next time, goodbye.